So Tom, the audience is yours. Go ahead.
Thank you. So yeah, okay, we can kind of maybe ignore the long title, and essentially what I'm going to be showing you is hopefully an approach that I'm using to try and get a little bit more immediate value out of some pXRF data that's being collected routinely. My project is part of a larger consortium project between the University of Leicester and Cardiff University. My remit is to kind of take the data science part of the project, and it's all funded by Anglo-American, so thanks to Anglo-American for the funding and for the data. And also, just whilst I remember, thank you to the organisers of this conference for letting me talk today. I think there's a lot of distinguished people talking today. I'm definitely not one of them, but hopefully you find this interesting the same. Okay. So you might have called the overall project called NL4D, Northern Limb in 4D. What is the Northern Limb? Well, it's the northern limb of the Bushveld complex. So any geologist any geologist here will probably be familiar with the Bushveld complex. It's the largest layered igneous intrusion in the world. It's in the northeast of South Africa. It's about 300 kilometers across. It's interesting for a variety of reasons, but economically it's very important. It's responsible for around 75% of the world's platinum production. So it's very well endowed in platinum group elements. Our project's focused specifically on the northern limb, which, as you imagine, is in the northern part of it. The northern limb is a little bit different geologically from the rest of the Bushveld complex. So to be honest, we don't need to know much about the geology for the rest of this talk, other than just remember it's just a layered igneous intrusion of largely ultramafic to mafic rocks. That's pretty much all we're going to focus on. So, as I mentioned, the project's funded by Anglo-American, and I've been given a lot of their drilling data. So they're actively drilling to extend their known resources in the area, and they're doing a lot of diamond drilling. So if you can pick out in this picture, there's actually 6 diamond drill rigs in a row, which I found pretty exceptional when I visited. So they're clearly recovering a huge amount of core. So the core that they recover is pretty boring, to be honest, and I'm not maybe the most enthusiastic geologist at times, but even I think really enthusiastic geologists may struggle to get excited by that. But what Anglo are doing on this project is immediately as they recover the core out of the hole, once it's been cleaned and dried, they're actually taking pXRF samples directly on the whole core. So pXRF, if you're not familiar, it's portable X-ray fluorescence. So it's a device which just zaps the rock with some X-rays, reads back the X-rays that get emitted in response, and then from that you can determine a geochemical analysis of the rock. So very quickly and very cheaply, which is a big benefit of this technique, but yeah, we can get a very large geochemical assessment of this hole immediately as it's been drilled. And what I've seen often with pXRF data, I think, is it's a very rich data set, and obviously we're getting it really quickly, it's the benefit of it, but maybe we're not necessarily processing it as quick as we're acquiring it, and then soon enough we've got our proper lab-based assays, maybe 3 months down the line, or a little bit longer perhaps, where it kind of ends up being superseded. And my thought is, if we're collecting this data immediately, it's maybe a good idea to maybe use it immediately. And I think one barrier to be using this data immediately is it's a large data set. I've only shown 7 elements there, but it returns 36 elements. Not all are usable, or many are below detection limits, but it's a very large data set. In this case, Anglo are taking samples between every 20 centimetres to a metre. So on an 800-metre hole, it's a lot of samples. So my thought was, perhaps we can try and convert the pXRF data into something that's immediately useful, like perhaps an overview of your geology downhole. So immediately as the hole's been drilled, if there's a backlog of logging core, we've at least got a core log, an overview of your lithology downhole, before a geologist even had a chance to look at it. Maybe on early exploration programs, this is not as useful, but I think as you get kind of closer and closer to production, where your things are speeding up, having this immediate feedback of lithology downhole might be quite useful. So it should be a straightforward enough task. We've got our sort of input vectors from our pXRF. We've got quite a lot of historical logging, which we could train a model against. So that's what I initially tried to do. So in this case, I used XGBoost, which is a gradient boosted decision tree. And that's the sort of result we get. So first impressions it's not necessarily that bad, so don't worry exactly what the colours are for now. I'll explain later, but you can assume that similar colours, similar lithology. It's not terrible. Maybe I should have ended my work there and just been happy with that. But I think what I was frustrated by was the noise that we're seeing in the logs. Basically, not only the misclassifications, those aren't always a problem, but it's the flip-flopping between two similar classes immediately next to each other, which is quite unrealistic in terms of how a geologist would log core. You lump bits together, typically, if they're similar. So that was what I tried to set out to try and improve upon. So what's the source of this noise in our classification, and what can we do about it, basically? So it's quite obvious if we think about taking pXRF samples on whole core, that depending on how coarse-grained the rock is, we're going to have some issues, because the sampling window of the pXRF device is pretty small, about a centimetre squared or so. And so on a finer-grained rock, like in that example there, those samples are going to be probably fairly representative of that interval, and those samples between them are going to be quite similar. But clearly, once we move into something that's more coarse-grained, in that instance, we're going to be having a response which is more related to the feldspar here versus the pyroxene there. So we're going to get two very different samples. It's going to not be representative of that interval. Repeated samples of that interval might be representative, but those individual ones are not. And when we're making a prediction for each individual pXRF sample, that's where the noise comes about. Similarly, if we've got veining, these are going to be problematic. So what can we do to improve this? I tried some initial approaches using moving averages, which is quite a common approach to add additional features to this sort of task. And it does improve the situation, but I thought there might be some other techniques that have been developed which may be able to improve the classification a bit better than just a simple moving average. So in my head, I thought what ideally we'd like to do is identify boundaries in our downhole data. So for instance, I haven't labelled this, I do apologise, but this is magnesium downhole from the pXRF, and this is the equivalent log from that same hole, right? So you can kind of begin to pick out clear boundaries in that magnesium data, which correspond to intervals in lithology. And I guess the idea is that hopefully if we could average the data in between those boundaries, then we would have a sort of a better representation of the lithology in between. So the question is, how do we find those boundaries? Didn't expect those lines to disappear. Oh, they're back. There we go. And there is a method that exists, which goes by a few different names, with the wavelet tessellation method, which is, I think, what most people know by. It's based on the continuous wavelet transform. So what the continuous wavelet transform does is it allows you to find boundaries in a sort of a time series or a downhole series of data, anything that's continuously sampled, regularly spaced. And it'll find these boundaries at different scales of observation. And this method has become very popular and quite well known because June Hill at CSIRO has built it up into a very nice method and applied this tessellation method onto it to basically create a plot which looks something like this. So your input is your pXRF, or whatever it is, in this case, our magnesium values downhole, and then our output is this tessellation plot. And the way to read this is the further the lines extend to the right of this diagram, the sort of stronger the boundary. So hopefully you can appreciate, for instance, this interval here is quite distinct, and likewise the boundaries bounding it, top and bottom, extend all the far across to the right. And it doesn't just do it for the major boundaries, it does it basically for any inflection point in your signal down, increasing sort of smaller and smaller scales. So, crikey, 5 minutes left. Wow, okay. I was going to...
Plus discussions.
Oh, is that... Oh, okay, so that would be 15 minutes.
If you don't want a discussion...
Okay, well, I'll stop contemplating. I am going to spend time talking just how the continuous wavelet transform works, because I think outside of the way I've applied it, it's a nice technique, and I think people might appreciate to know how it works. So it's basically a convolution, if you're familiar with that sort of thing. You take a wavelet and you run it down your signal, and it creates essentially another signal. And you keep on doing this with increasing widths of wavelet. And we carry on doing that, and we don't just do it for a number of which, we do it continuously across all widths of this wavelet. And so when you join them up together, you end up getting this thing called a scalegram, which in itself isn't too sort of useful, but if you use a particular type of wavelet, specifically the second derivative of Gaussian wavelet, where that scalegram equals 0, if you remember anything about derivatives, second derivative, 0 value equals, it will find the location of an inflection point in the original signal. So the 0 values on that scalegram find our locations of our boundary. We then transfer those boundary locations onto the first derivative scalegram, and from that we can extract our boundary strengths. So now we have location of boundaries and boundary strengths. And when you add those two bits of information together, plot them down whole, you get sort of all these boundaries and boundary strengths, add in a few more lines, and you have your tessellation plot. So that's the sort of mechanics of that overall process. So how do we use this to improve our classification? So, as you previously seen, you create a tessellation plot for an output from the pXRF, and I've just shown it for magnesium, but I'm doing it for multiple elements out of the pXRF. Calculate mean within all those intervals, and I actually also calculate the variance within those intervals and use that as a feature. Extract along those dashed lines what you can call a pseudolog from that tessellation plot, so it's the interval data basically with the mean values or the variance values for these intervals. And we then basically append that data back onto our original data set. So we have our original magnesium values, but now we also have magnesium, the mean of magnesium at that scale interval, and at that scale interval, and so on and so forth. So you actually end up with quite a large number of features, some of which we can disregard because they're very similar, but anyway. So let's just skip the model setup, just two papers there which kind of explaining why I'm using decision tree-based algorithms. You can check them out. I don't have time, I think, to talk about it now. But model set is fairly standard, splitting off some of our training and testing data. As I mentioned, I'm using XGBoost for the actual model. But let's just jump into the results. I'm just going to mention elephant in the room. These accuracy numbers don't look too great at first impression. I think that's probably what a lot of people are thinking. I'm going to probably spend the rest of my time now, a limited time, trying to explain why I actually think they're okay. But hopefully you can appreciate, so the logged is on the left. My prediction with the engineered features on is in the middle, and then the prediction with the samples is on the right. So numerically, whilst the accuracy is low, the engineered features do improve the situation. But where is this low accuracy coming from? And if we go into the confusion matrices, I'm going to skip through these. A lot of the confusion is coming from very similar lithologies. So I am trying to classify a large number of lithologies here, which is part of the challenge. And a lot of these lithologies are very similar. So if we just focus on these down here. So these four different lithologies are essentially ultimately the same. It's just a sliding scale between entirely pyroxene and entirely anorthite. And so confusion between these is going to be quite likely. And then the question that we've got to ask is the error coming from the logging that we've trained our model from, or is it actually a problem with my model? And I can't answer that for sure. It's probably a bit of both, but I definitely think there's a large component of error in the logging. And I guess that's somewhat what motivates this whole piece of work, is that a bit like Charlie touched on, we are trying to split these rocks into classifications when perhaps actually modelling it as a continuous range of properties would be a better approach. And that's something else that I'm working on, is rather than just modelling all these different types of gabbronorite, which are very similar, perhaps we should just model it, okay, it's a gabbronorite, or it's this, all those brown and yellows would be the same, and then I've trained another model on some hyperspectral data to predict mineralogy from the same data set. So then we could have a sort of regression model which shows us, all right, how felsic is this, or how much pyroxene, and you can actually then begin to say how much of that pyroxene is clinopyroxene versus orthopyroxene, and so you'd have a sort of a simplistic log and then more and more detail with these regression models. It's the same story for serpentinization. A lot of the confusion between, is it serpentinite or is it serpentinite felspathic pyroxenite? Well, where one geologist will log one, another will log the other. And so that's where ultimately a lot of this error arises. So if you actually combine a lot of these lithologies that are confused in the confusion matrix that make geological sense, and you can imagine perhaps instances where the logging is getting confused, then the model accuracy jumps up to about 75 to 80%. I also think it's interesting to note that some of the highest and most sort of the best predicting lithologies, which are these granites, granophyles, dolerites, this calcosilicate, and this very unique kind of distinctive poikilotic anorthosites, just for its particular texture. It's an anorthosite with a particular texture. These are going to be probably some of the lithologies which are most consistently logged by the geologists. So the logging in those instances is the most consistent, the most accurate, and I don't think it's a surprise that also then the model is finding those to be the easiest to predict. I'm not sure how much time we're on now.
5 minutes,
Oh,
if you don't want questions.
Oh, no, questions are always nice. I think the rest of it is just going through. I've got hundreds of holes, so I can't show you. Sorry, I haven't got hundreds of holes in. No, I haven't got hundreds of holes in my talk. I've got hundreds of holes that I could have chosen from. But I think it's a nice illustration here of sort of where we're not getting this flip-flopping of the different rock types, the prediction using the samples only versus the prediction using the engineered features is a bit of a cleaner log. I hope you'd agree. Admittedly, it's actually missing out some very thin intervals of granite there, but we're not getting misclassification of poikilotic anorthosite, which is quite important because the poikilotic anorthosite is quite a key marker bed. So, and then in this critical zone down here, I'd say the match is pretty good, but the improvement's less down here. That's where they've got more data. The spacing of the data is closer here. More logs. So I think I'll draw some conclusions here before I lose my train of thought anymore. Essentially, I think, whether or not this is the right approach, I think we should try and make most of this pXRF data in a quick way, and this is one way that might help. I think this workflow is most effective in cases of simple geology and consistent logging. That probably applies for every machine learning problem. Simple problems, simple solution. The engineered features do improve the accuracy and minimise that noisy log issue. Not sure if it's necessarily the best technique to use, but it was the one that I chose. Clearly, the addition of more data is going to drastically improve this. And data, if we were to continue the theme of data that's quickly and cheaply acquired, the obvious one's photos, and there's plenty of work out there. There's people from DataRock here I know that, and DataRock does some brilliant work around extracting things from photos, improving core logging accuracy, but obviously that does increase the complexity of the workflow somewhat. And my last thing, I just mentioned there, I have a feeling perhaps this requires a bit more work to determine this is the case, but I like to think the model is producing a sort of wisdom of crowds prediction. One of those papers that I cited but I didn't mention, a student at Vasili's actually showed how you can inject a lot of noise into your logging data that you're training a model on, and decision tree-based algorithms will quite handily just disregard that noise, the noise being misclassified, mislogged intervals. And so I think it's quite likely that there is a chance that we are producing a sort of wisdom of crowds by incorporating all of these different geologist logs in the training. And yes, that's about it. Any questions?
Thank you, Tom. For a comment, I really like your term, natural confusion.
I don't even remember saying it, but yeah, go for it.
Yeah, I think this is really a true output for me from your talk, that we should actually excuse the machine learning algorithm for confusion, which would be allow for geologists to confuse, and you referred to geologists, right? And this is good uncertainty. That's interpretive and relative interpretation uncertainty, which is very difficult to quantify, while the kind of unacceptable confusion where you actually hit the different facies, and that would actually maybe derail the whole perspective. Yeah. So I think that's a big conclusion.
Yeah, I think there's probably more nuanced metrics I could use as well. It's sort of custom metrics to quantify, to quantify the accuracies of model.
So we have 2 questions in waiting. First, Mark, please.
Thank you. Tom.
Thanks, Mark.
You mentioned that you calculated the variance between different intervals.
Yeah.
Did you notice there was a relationship between that and, say, some of the lighter elements that you were using?
That's a good question, because, yeah, the pXRF is poor when it comes to lighter elements. Off the top of my head, I didn't. What initially drove me to do that is I picked up on a correlation between the variance of manganese and serpentinization, which is driven, I think, when you have olivine serpentinized, one of the byproducts is manganese, and it has nowhere to sit in the crystal structure of serpentinite. And manganese being it's quite mobile, it leaves. So that was the initial, I was like, oh, maybe I should include variance. And manganese variance was in my kind of top features for the model. Things like magnesium, which is the lightest, didn't appear in the kind of feature importance. So, yeah, some of them may be noisy because of the measurement error, rather than, but I haven't actually picked up on it. But that's a good point. Maybe I should check out. Yeah.
There was another question, and this should be the last, if you forgive me, because then we have another talk, and then we have a picture, and then we have lunch. So, but during lunch, we can buttonhole Tom and talk and ask more questions.
Buttonhole me away.
So
Yeah,
please.
cheers, Tom, for a good talk. Just a quick question. It's like, obviously, depending on the geologist who's doing the logging, you link that, and then if you had one consistent geologist, did your axes improve? And then that opens up like the geotech automated sampling type. And will that improve your model?
I didn't want to target anyone in particular, and I would like to actually, no, but quite an important thing I'd like to just say actually, all joking aside, I didn't collect any of this data, the geologist from Anglo American did, and I've been out there and looked at this core. I mean, I'm a bad logger, there's people I worked with in Australia here who corroborate that probably, but like I couldn't do what they did, incredibly skilled, like really detailed logging. I couldn't pick up on half the things they pick up on. And so I don't want to make this sort of a thing of geologist logs are bad and machine learning's good. I did pick up on one thing. I did iteratively train the model with increasing amounts of drilling data. And I did pick up on there was some distinct jumps, both positive and negative, in the accuracy as you include more and more holes. I think that's probably because you are going from, one geologist logged this hole, and then we've introduced a new level of uncertainty. We've added a new geologist into the data set. So it does have an impact. I haven't gone down the road of really interrogating that. But yeah, as just a slightly closing statement, on the theme of, I don't want to also give the impression that I think we shouldn't be logging. Clearly, my model's pretty shit, so we can't get rid of the geologist yet. But also, it's trained on logging data, and also, logging has a purpose for a geologist to learn about the rocks. As an objective way of collecting data, it's pretty rubbish, but as a way of familiarising ourselves with our deposits, picking up on things that are really important in the rocks, it's invaluable. So I don't want to give the impression that we shouldn't be logging core. I just don't think we should use it for objective data collection.
Okay, nice final words by Tom.
Thank you.
Thank you.